This question comes from James, who asks, if the Earth had always had two moons, what would actually be different? Before getting into the consequences, it's worth noting that this question may be less hypothetical than it sounds. In 2011, planetary scientists Eric Asfog and Martin Utzi published a study in Nature proposing that Earth actually did have two moons early in its history. The collision that formed our moon between Earth and a Mars-sized body about 4.5 billion years ago likely produced not one body but two. The large moon we know, and a smaller companion roughly 750 miles wide, about one-third the diameter of our moon. Their computer simulations suggested this second moon sat in a gravitationally stable position for tens of millions of years before eventually drifting into its larger sibling in a slow collision slow enough that instead of blasting a crater, it simply piled material onto what is now the far side of the moon. The moon's far side is noticeably more mountainous and has a significantly thicker crust than the near side, and that asymmetry is otherwise difficult to explain. So two moons in the early sky is not science fiction. It's a serious scientific proposal. What it means for us is that the more interesting version of James's question is not, what if we somehow gained a second moon tomorrow, but what if that second moon had survived? The first and most pervasive consequence would be the tides, and they would be dramatically more complicated. Our tides today already produce a rhythmic, twice-daily cycle that every ocean creature, every coastal ecosystem, and every mariner throughout history has had to reckon with. Two moons with different orbital periods, different speeds around Earth, different distances, different positions at any given moment, would generate two overlapping tidal cycles that would rarely sync up and never quite repeat. The combined tide at any location would be the sum of both moons' gravitational pulls on the oceans, and depending on whether those moons were pulling in the same direction or working against each other, you'd get either extreme high tides or tides that nearly cancel. Neil Cummins, a physicist at the University of Maine who has thought carefully about this problem, estimates that a second moon-sized body at a closer orbit could drive tides up to 8 times higher than our current ones. Even a smaller second moon at a more distant orbit would make the pattern irregular enough that predicting tides, which today sailors, fishers, and port engineers have been doing for centuries, would require considerably more calculation and considerably more uncertainty. The night sky itself would be transformed. Two moons moving at different speeds would create a constantly shifting arrangement, sometimes one rising as the other sets, sometimes both up at once, sometimes both new and absent. There would be fewer, truly dark nights. The kind of deep darkness that shaped human astronomy, the darkness in which you can see the Milky Way as a solid band, would be rarer. It's worth thinking about what this might have meant for the development of ancient astronomy, since so much early science depended on careful observation of stars that are drowned out by lunar light. But the deeper consequence, and the one least obvious at first glance, is axial stability. The current moon acts as a gravitational anchor on Earth's rotational axis. The torque it exerts on Earth's equatorial bulge prevents the planet's tilt from wandering too far under the influence of Jupiter and the other planets. Without the moon, research published in Nature in 1993 by Jacques Lascar and colleagues showed that Earth's axial tilt, currently sitting at a steady 23.4 degrees, could potentially range from nearly 0 all the way to 85 degrees. Mars, which has only tiny moons, has an axial tilt that varies chaotically between roughly 0 and 60 degrees over millions of years, and scientists have suggested this is part of why Mars appears to have had periods of flowing water followed by extreme aridity. A second moon would add additional gravitational torque on Earth's axis, but two moons pulling from different positions and at different periods could also perturb each other's orbits over geological time, making the long-term dynamics of the whole system harder to predict. The axis might be more stable, or the interactions might drive instabilities that a single moon doesn't produce. This is an area where the answer is genuinely not settled. What we can say with confidence is that the oceans, the coasts, and the life that evolved alongside them would look entirely different. The intertidal zone, the strip of coastline that gets covered and uncovered by tides, is one of the most biologically productive and diverse environments on Earth, and it exists precisely because tidal rhythms are regular enough that species can time their reproduction and feeding around them. Horseshoe crabs spawn in sync with specific high tides. Coral spawning is coordinated by lunar cycles. A second moon would make these rhythms more complex, and evolution would have had to find different patterns to lock onto. Whether that means more diversity, less diversity, or simply different diversity is a question biology can't fully answer. We do know that Earth came very close to having this situation. The evidence is probably sitting on the far side of the moon right now. Baked into the thick crust of the lunar highlands, a record of a collision that ended a two-moon system before anything alive was around to observe it. When you look up at the moon on a clear night, you're seeing what's left of both.